Welcome to Welcome to Pre-Calc, Lesson 1.2, Analyzing Graphs of Functions and Relations. Much of this section was covered in the summer packet, but some key concepts that we're not covering were determining the symmetry or types of symmetry of relations, and there can be those types of symmetry for some functions as well, or some types of symmetry for functions, and identifying even and odd functions. Today you did an exploration where you looked at the types of symmetry. You explored three types: y-axis, x-axis, and symmetry with the origin. Both relations and functions can have some of these types of symmetry. You saw that in your exploration. You noticed from both the table and from the vertical line test when graphed that x-axis symmetry can only happen for relations, not functions, whereas y-axis symmetry and origin can be for both relations and functions. Relations and functions can have both. X-axis can only be relations. In this video, you also, in today's explorations, were able to look at the difference between even and odd functions. Some of you got a little further in that exploration than others. Using the graph of each equation to test for symmetry with respect to the x-axis, the y-axis, and the origin. Support your answer numerically, then confirm algebraically. You can see that this one is definitely an x-axis symmetry, not y and not origin. The test, there are algebraic tests for this, is that if we look at the equation itself, you wrote down in your exploration that when there's x-axis symmetry, it's the y-coordinate that changes signs. Well, there's a test for that. If you plug in the opposite of y into the equation, so for this one right here, x minus y squared equals 1. If you plug in for every y, for y you plug in the opposite, and you get the same equation, then it has symmetry with the x-axis. So let's take a look. X minus y squared equals 1. But we have the opposite of y. When I square negative y times negative y, I get positive y squared. So I'm right back to x minus y squared equals 1. The same equation. Because they're the same equation, this has symmetry with the x-axis. So for symmetry with the x-axis, the test is to replace y with the opposite of y. And if we get the same equation, the original equation back, then it has x-axis symmetry. If we don't, then it does not have x-axis symmetry. Similarly, for y-axis symmetry, if we replace the x with the opposite of x, and we get the original equation back, then it has y-axis symmetry. So let's look at that. For this function. For letter B. Does it have x-axis symmetry? We're going to test for x-axis symmetry. It appears to. You can see that if you folded that semicircle, it would fold right on top of this one. In the equation, we're going to replace, we have x squared, we're going to replace y squared with the opposite of y. And when we square it, we're going to get y squared. So we have the original equation back, x squared plus y squared equals 25. Since it matches the original, it has x-axis symmetry. Yes to x-axis symmetry. Next, I'm going to test for y-axis symmetry. To test for y-axis symmetry, we plug in the opposite of x. So I have the opposite of x squared plus y squared equals 25. Whenever I raise a negative to an even power, I'm going to get a positive. If I raise it to an odd power, then it would stay negative. So this is positive x squared plus y squared equals 25. Since it meets the equation, it matches the original equation, I can say yes, this has y-axis symmetry. These are the algebraic tests for x and y-axis symmetry. From your exploration, if you remember, symmetry with the origin had both x and y, they switched signs. So the test for that, for origin, is to replace both x and y with the opposite of x and the opposite of y respectively. And if we get the same equation back, then it has symmetry with the origin. If we don't get the same equation back as the original, then it does not have symmetry with the origin. So for example, we're going to test for origin for letter B. Going to replace x with the opposite of x and y with the opposite of y, and see if we get the original equation back. The opposite of x squared is x squared. The opposite of y squared is y squared. So for this problem, in fact, we do get the original equation back. So we can say yes, this graph, although it's not a function because it wouldn't pass the vertical line test, does have symmetry with the x-axis. We've shown how to justify that algebraically. It does have symmetry with the y-axis. We've shown how to justify that algebraically. And it does have rotational symmetry. We've shown that algebraically as well. You will need to be able to show these tests on an assessment, showing algebraically that it has these symmetries, not just by graph. On the topic here, neither of these are functions. This is a relation and this is a relation according to the vertical line test. And we can see that for many of the x's, there is more than one output, more than one height. So while they have symmetry, they are not functions. It is possible, if you remember from your explanation, to have y-axis symmetry and be a function, and have origin and be a function. And when it does, then we call those functions even or odd. In your exploration, you saw how this relates particularly to polynomial functions in their degree. The algebraic test to determine whether a function is even or odd, some of you even got to in the table. You take your function f of x, and you're going to put input the opposite of x. So basically, you're going to do f of the opposite of x. For every variable in the equation, you're going to put in the opposite value in parentheses. Now, if you do this and you find that after you have simplified it, you find that you get the original equation back. So in other words, it equals f of x, the original equation after you plug in the negative, then it is said to be even. Whereas if you plug this in and you get all opposite signs from the original equation, then it is said that you have the opposite of the function, or the negative of the function, then it is said to be odd. Let's look at a couple examples. Identify these functions as even or odd. This one appears to be, at first glance, just looking at the degree, odd. It is possible for it to be neither, though, as well, so we have to be careful of that. So we have x cubed minus 2x. When I do the test, I'm going to plug in the opposite of x. I have x cubed minus 2 times x, and I'm going to plug in the opposite of x. But when I cube a negative, it stays negative. And when I have negative opposite of x times negative 2, that gives me positive 2x. Looking at these, the sign on these is the opposite of the sign in the original for every single term. Because of that, we get that it is the opposite of x, or opposite function, so the opposite of the function, so it is considered to be an odd function. For the next problem, when I perform this test, and I just plug in the opposite of x into the whole function, x to the fourth plus 2. When I plug in the opposite of x and raise it to an even power, it becomes positive. So I've gotten the same as the original function. Here in the example A, they were the opposite signs on all. Here it's the same exact function. So this one is equal to the original function, and it's said to be an even function. And our last example. At first glance, seeing the degree of the polynomial, we may think that it's odd, and it might be. But when we plug this in, let's take a look and see what happens. We're going to do f of the opposite of x and see what we get. When I cube that, it stays negative. So far, this looks odd. When I do the opposite of x times negative 3, that becomes positive. So far, this looks odd because these are opposite signs from the original equation. But when I square this, it becomes positive x squared, and this stays negative 0.5 x squared, or negative 1/2 x squared. That right there is the problem. Because while the others are opposites, these ones are not opposites. So not all opposite signs, and not the same function. Since it's not the same function, it isn't even, and since there's not all opposite signs, it's not odd, it's neither. This concludes the summary of the differences between even and odd functions, which are something you explored today in class, and how to determine whether a relation or function has y-axis, x-axis, or symmetry with the origin. Have a great day.